The first one has to do with acids and base. Here we have this particular chemical, HCO3. And for HCO3, remember that HPCO3 minus 2, PO3 is called phosphite, PO4 is called phosphate. When you put a hydrogen in front of phosphite, it becomes biphosphite. Anyway, the question here is include the phase, and for each chemical, write the reaction of these ions in water. So what happens when you take this particular chemical and you put it in water? What is the reaction? This chemical can either attach another hydrogen or lose that hydrogen. Okay, so that's the reaction. Include the phase of this reaction, identify and label the conjugate pairs in your reaction, and write the equilibrium constant for each of the reaction. The other thing that you guys will need to do is look in the appendix of your lab manual, because in the appendix, you go to Appendix 9, and that's what you guys will be using for this particular question. In Appendix 9, you're going to find this this chemical right here, HPO3, comes from the original acid H3PO3. How do you know the original chemical? Because this is an acid, and the original chemical is going to have a hydrogen attached to it. When you lose one hydrogen, you get H2PO3. When you remove two hydrogen, you get HPO3. And when you remove three hydrogen, you get H. You don't even get H, you just get PO3. So that's what this is, okay? What we have is phosphorus acid right here. The first hydrogen comes off with a equilibrium constant of 3 times 10 to the minus 2. The second hydrogen comes off with a rate constant of 1.62 times 10 to the minus 7. The third hydrogen does not come off. And the reason why the third hydrogen does not come off is because that third hydrogen in that formula isn't attached to an oxygen. So this particular chemical only has two ionizable hydrogen. So when you write this chemical in water, don't write PO3 minus 2, because that's not a possible chemical. What probably happens is that this is going to be acting as a base. It's going to be accepting a hydrogen, in which case you're going to see HPO3 minus 2 plus water goes to H2PO3 plus hydroxide. Okay, this one right here, the acid that forms this is going to be HF, and you can find hydrofluoric acid in here. Here it is, and the chemical, when HF gives up one hydrogen, has an equilibrium constant of 6.8 times 10 to the minus 4. Of course, that we don't have HF here, we have F minus. So that means F minus will react with water and remove the hydrogen from water, because now F minus is a base. It's going to remove the hydrogen from water, form hydroxide and HF. So that's going to be a base chemical reaction where it's a proton acceptor. This is bicarbonate. Bicarbonate, the chemical is going to be from carbonic acid, and you can find carbonic acid right here. And it's got two ionizable hydrogen, H2CO3, that's the first one, and that's the second one. So you can take a look at this and see what type of chemistry will occur when you put it in water. That's basically what you guys are going to write down for that first question. Write the chemistry that occurs, identify and label the conjugate pairs. And we haven't covered the conjugate pairs yet. That's why this particular assignment's not due until next week. It's not due Sunday, because for those of you in lecture, you guys need to understand what conjugate pairs are. If you want to look ahead, go to 16.02 in the Zoom video, and I explain what conjugate pairs are. But this one, there's no calculation involved. It's mostly conceptual. You got to understand what happens to these chemicals when you put it in water. The reason why you need to know what happens is because you won't be able to set up the problem until you know the chemistry. It's all about knowing the chemistry. If you don't know the chemistry, then you can't write the correct mass action expression. Okay, that's why it's important to understand the concept. The second problem here, okay, second problem here is phenoxide. Phenoxide is going to be the conjugate, that is the acid without the hydrogen of phenol. This is phenol, C6H5OH. When you remove the hydrogen, you get phenoxide. That's this chemical right here. That's why it's got a negative, because the hydrogen's removed. It's a base. In other words, it has an attraction back to that hydrogen it just lost. It's a weak acid. So that means that it can also accept the hydrogen it just lost. And if it accepts the hydrogen it just lost, then it's a weak base. And I tell you what the K equilibrium for that reaction is. It's called a KB because it's a base reaction. It's 7.7 times 10 minus 5. What is the Ka of the phenol conjugate of phenoxide? You could have seen it in the appendix, or you could do a calculation of how to calculate the conjugate just based on the fact that Kw is equal to Ka times Kb. That's another relationship that we're going to be establishing. So you guys will be able to do that just from this value right here, 7.7 times 10 minus 5. If you just take Kw, which is 1 times 10 to the minus 14, we're always going to assume 25 degrees unless otherwise stated. If you take 1 times 10 minus 14 and divide by 7.7 times 10 to the minus 5, you get the Ka. And you can double check your work by looking at phenol right here and making sure it's in the correct ballpark. These numbers fluctuate depending on what textbook you have, but as long as the exponent are the same, you're in the general ballpark, okay? Calculate the pH of 0.5 molar of this particular solution. This is a base. If this is a base, then it's going to react with water to form hydroxide. You can calculate the concentration of hydroxide from that reaction. If you can calculate the concentration of hydroxide, you can calculate the POH. If you got the POH, you can calculate the pH. Okay, so even though it's a basic solution, you can still calculate the pH of the solution. This is the same thing. You've got trimethylamine, and trimethylamine is going to be, I believe, if it's not here, then it's because, yeah, it's not here. Trimethylamine. Yeah, here it is. Trimethylammonium. This is the chemical right here. It's got a Ka of 1.58 times 10 minus 10. I tell you what the pKa is. If you take this number, 1.58 times 10 minus 10, take the negative log of that, you should get to this value right here, very close to it, okay? Will it be higher or lower than, you think that the pKa is higher or lower than 1 molar phenol? So you just have to compare that to phenol. What is the difference in pH for the two acids? I'm referring to phenol, that's the acid, and I'm referring to trimethylamine, that's the acid. So when you have 1 molar solutions of both of these chemicals, which will give you the higher pH, and what's the difference in pH? Okay, so that's that question. This second question right here, let me get this out of the way, is about something that we like to call polyprotic acids. Poly means many, protic meaning hydrogen. So a chemical that has more than 1 hydrogen is considered polyprotic. When it's got 2 hydrogen, more specifically, it's considered diprotic. H2S is diprotic. H2SO4, sulfuric acid, is diprotic. Carbonic acid, H2CO3, is considered diprotic. When you have 1 or more, it's also considered polyprotic. So sulfuric acid is not only diprotic, it's also polyprotic. Phosphoric acid, H3PO4, that's considered triprotic or, again, polyprotic. So we have this acid right here, H2S. And what you have is, the thing about acids is that they don't lose their hydrogens simultaneously. Okay, you don't just go H2S and go to 2H plus S minus. They do it sequentially, because each time it loses an hydrogen, it does so with an equilibrium. So the second hydrogen doesn't get removed until most of the first hydrogen is removed. That's why you have two equilibrium constant for a diprotic acid. So this is the chemistry. H2S will lose one hydrogen, but you get the HS, what we call conjugate, left over. This equilibrium happens to have 5.7 times 10 to the minus 8 as its Ka1. That's a 1 right there. Then once most of H2S has lost its first hydrogen, now the HS is going to lose its next hydrogen. Okay, so this is the second hydrogen that comes off, and you get S minus 2. And look at the equilibrium constant. It's much smaller. That's because removing a hydrogen from a negative anion is going to be much more difficult. That's why that equilibrium constant is much smaller. It happens to be 1 times 10 to the minus 9. So you have two, the math is easier because you don't have chemicals to the third power anymore. Your mass action expression will never have anything to the third power in acid-base chemistry, because instead of giving you equations to the third or fourth power, you have multiple equations in which one hydrogen is removed one at a time. So this is a reaction in which you have to solve this first equilibrium, get the answers, what the concentration is in this equilibrium, so that you can put it into the second equation and then solve for that. So it says right here, calculate the concentration of HS in 0.22 molar H2S. So that's an ice table. You write 0.22 molar initial for H2S. You have 0 and 0 here. In the course of the reaction, this is minus X, this is plus S, plus X, and plus X. So the mass action expression that you guys will see is going to be somewhere in the order of the appendix is where you're going to find the KAs. Okay, so let me just put this right here, and you guys should be able to see my sticky. So this problem right here becomes the following. You have Ka1, and that's going to be equal to 5.7 times 10 to the minus 8. And that equals to the product. And that product is H plus and HS minus. And that's divided by H2S. And I need to put brackets here because that's going to be the concentration of these chemicals. Okay, so that's your, and I apologize if that's small. Let me see if I can't make the font bigger. Let's see, bigger. Okay, bigger. So let's see if I can't do that. So that's what you have. So remember that the initial concentration here is going to be, according to this problem, it's going to be 0.222 minus X. That would be this line right here. This would be, again, you guys know how to solve this because you've already understand equilibrium. This will be X, this will be X, and that'll be 0.222 minus X. Now you can just solve that mass action expression. Once you find X, okay, then that'll be the concentration of HS. You use that answer for the second equilibrium. Once you figure out X, that's the hydrogen ion concentration, you can calculate the pH from that. So this second problem right here, or this problem right here, is nothing more than using the concepts that you learned from chapter 15, but now to solve acid-base problems. It's basically equilibrium problems. This one's a little bit tricky. What the key to doing this problem is write the mass action expression for this. What you want to do here is it tells you that you have methyl red. Methyl red is a common acid-base indicator. So when you, I don't give you the formula, but the formula is not important. Just write it this way, okay? You've got a hydrogen, and this will be the, this thing will break down to hydrogen and its conjugate, like that. So any acid will remove a hydrogen, and then what's left behind is generally its conjugate. That's the chemical without the hydrogen. So that's the chemistry. It tells you right here that the Ka for this equilibrium, so it's a double arrow actually. Okay, it's a double arrow. But it tells you that the Ka for this equilibrium 6.3 times 10 minus 6. So in other words, this indicator is a weak acid. How do you know it's a weak acid? Because the Ka value is less than 1. Its undissociated form is red. That makes this guy red. That's what this problem is telling you. This guy is red. That's the undissociated form. Its dissociated form, that's this guy, because hydrogens are transparent, is yellow. Okay? What color will methyl red solution, that is with this indicator, have at pH 7? Share your calculation and explain your answer. Whenever you see a number like the pH and it's given to you, that's the, you can get the hydrogen ion concentration at equilibrium. Because when you read a pH, the solution, the reaction has already stopped, it's at equilibrium, and the pH tells you how much acid you have. So what you need to do with that number is take it to 10 to the minus pH, and that'll give you your hydrogen ion concentration, and that's what this guy is right here. All you've got to do is solve for the rest. So once you understand the approach for this particular problem, the problem really becomes super easy. Okay. On the next page,
A question, Professor?
Excuse me.
what's up? Yes.
So I'm sorry. So in our lab manual, it is not the methyl red, it is the phenyl red in mine at least, and it's acid-base indicator, and it has a pKa equal to 8.
Okay, so if you got a pKa equal to 8, then the Ka is 1 times 10 to the minus 8.
So that should be okay. Is that correct?
Yeah, the problem's the same. I just changed the problem kind of like once a year so that you guys are not just copying someone's old lab report and all that, but the concept's still the same. Concept's exactly the same. What you want to do is take that phenol red, break it up like this right here, except now it's going to be hydrogen plus pH, phenol red, okay? And then this will be PR. You don't know the formula. The formula is not important. You just need to know the chemistry. And if you know what the Ka is, then you can write products over reactant equals the Ka. And then you can figure out which number is bigger. Is this number, sorry, this is a P. Is this concentration bigger than this concentration? And whichever is bigger, it'll tell you what color it is. The chemical that's more dominant will determine the color of that solution. Does that make sense?
Yes, thank you.
Okay, well, thanks for correcting me. Moving along, okay. This you can just read from your lab manual, or I don't think I think your lab manual tells you about buffer capacity. It's also in your textbook. Buffer capacity is really how much chemical do you need so that when you have that chemical in there, the pH of the solution doesn't change. A buffer is a chemical that will, if you contaminate that solution, or if you put in some other chemical in that solution, the pH will not change within 1 pH unit. So what happens is that when you put a contaminant in there, the added chemical that you add is going to remove the hydrogen or remove the hydroxide so that the pH of the original solution doesn't differ very much. That's why we call it a buffer, because buffer absorbs the hydrogen ion or the hydroxide ion so that the pH doesn't change overall. And you guys who are in biology, you're always working in buffer solutions. Why? Because it's critical to work in a very narrow pH region. So this particular question has to do with buffer capacity. How much of that external chemical do you need to add before the pH is going to, before that chemical gets used up, and now the pH is going to be altered. That's the buffer capacity, okay? What is the effective pH range for the sodium acetate, acetic acid buffers? Buffers, by the way, are best formulated based on the acid and its conjugate that makes it up. And you might ask yourself, well, how do I get a conjugate into a solution? The conjugate are like the following. Suppose I want to form a buffer with carbonic acid. Well, then I would take sulfuric carbonic acid, this guy right here, and I would mix it with sodium carbonate. And the reason why I would do that is because you guys know that sodium carbonate is going to break up to sodium, which is a spectator, two of these. So it's not going to do anything to the solution, but it's also going to form carbonate ions. And because it forms carbonate ions, that means that the chemistry of carbonic acid in this buffer solution is the following. See this sodium carbonate? Well, that's a common ion right here. And because it's a common ion, it's going to cause this equilibrium to shift to the left. You've got carbonic acid, so the reaction is going to go to the right, but the common ion will cause this equilibrium to also go in the reverse order. And by doing that, going in the reverse order, you also don't allow the hydrogen ions to increase. Any chemical that increases the hydrogen ions, this chemical right here will eat it up and form carbonic acid. Because remember, what changes the pH of the solution? It's not carbonic acid, it's not carbonate ion, it's hydrogen ion. Because the pH is defined by negative log hydronium ion. So anything that makes the hydronium ion go up or go down will change the pH. This chemical is not hydronium ion. This chemical is not hydronium ion or hydroxide ion. So the pH, by introducing these chemicals, will not change. If this changes, however, then the pH will go up or down. You got to look at the definition of pH. pH is equal to the negative log of the hydronium ion. If you change the hydronium ion concentration, you change the pH. If you change the hydronium ion concentration, you change the hydroxide ion concentration, because they're always going to be at a certain multiple of each other, okay, because they have to equal Kw. So when you change the hydronium ion concentration, you also change the hydroxide ion concentration, which changes the pOH. These chemicals here, bicarbonate and carbonate ion, will not change the pH. The hydrogen will. Same with this question right here. You got sodium acetate. So sodium acetate is NaCH3COO, the acetate ion, and acetic acid. Acetic acid is the acid in vinegar. Again, they're conjugate pairs because they have common ions. So you treat it like what I have here, except write acetic acid here, hydrogen ion here, and acetate ion here. Okay, and I tell you what the Ka is, and so you can figure out what the effective buffer range is. The effective buffer range is always going to be based on the Ka, the pKa plus or minus 1 unit. So that's basically what we have here. The second question right here, calculate the pH that is 0.45 molar carbonic, this right here is acetic acid, and 0.75 molar sodium acetate. So It's basically a common ion. What you have is this right here, HC. I'm just going to abbreviate it as that. That's our abbreviation for acetic acid. AC stands for acetic acid. Rather than writing all this down, okay, the chemistry is not the hydrogen in CH3 or the oxygens here. The chemistry is about the hydrogen in acetic acid. So I can abbreviate it, and that's what you see a lot of chemists do, and write this reaction. Guess what? You have the initial concentration of that, so that'll be in the initial line. So in the initial line, you would put, this would be 0.45, because that's you got to be able to read what the question is providing you. Calculate the pH of a solution that is 0.45 acetic acid and 0.75 sodium acetate. That's the initial. It doesn't say that's the equilibrium. So it's a common ion. This is 0.75. Then the change will be minus X. This will be plus X. And this will be plus X. And then you can make simplifying assumption. Why? Because take a look at the Ka of acetic acid. The Ka of acetic acid is 1.8 times 10 to the minus 5. That's a very small number. So you can make your assumption here that 0.75 plus X is 0.75. You guys can solve the equation for X. X is the hydrogen ion concentration. You can calculate the pH from that. So again, we're using our knowledge of equilibrium to solve these acid-base problems. That's why I told you that equilibrium is such an important topic, because it stretches different amount of chemistry. And it does so a lot in acid-base chemistry. So this problem is not so difficult in terms of solving, because we covered the common ion effect in chapter 15, and that's what buffers are. They're common ions. This next problem, okay, this is what we call a titration type problem. I'm going to skip this for now, and I'll go over it next time, or you guys remind me to go over it next time, because this really is an important topic when we look at titration curves, because this is a problem on titration curves. So I'm going to stop, skip that for now. These last two problems, it says, look up the formula for chloroacetic acid, carbonic acid, and citric acid, and you will find that over here, okay? Chloroacetic acid is going to be right here. Carbonic acid, we already covered that. And then citric acid is right here. So rank the following in order of increasing POH, not pH, but POH, if you've got 0.1 molar concentration of all these acids. So that just means that you have to set up the ice table for each one of these chemicals and calculate the pH. And then remember that pH plus POH equals pKw. So you can calculate POH that way. So that's that question. I just want you guys to practice calculating pH or POH in that problem. Second problem here, okay, rank the following in order of increasing pKa. And this is mandelic acid, maleic acid, and malonic acid. So I think one of these are missing. This is maleic acid, okay, malonic acid, and mandelic acid. So all the acids are here. So that, again, doesn't require any math. You just have to understand the concept. So I think that's your activity for acid-base. A lot of the concepts, especially this problem right here, we haven't talked about yet, but we will do so starting next week. And that's why this isn't done until the following week, okay?